Good day, my name is Timothy Adekunle. I'm here to discuss how to use moment generating function to prove some distribution. I would like to start from binomial distribution. The PMF of binomial distribution is f into bracket s equal to n combination s, p raised to power x, q raised to power n minus x. Our moment generation function formula is m into bracket theta equal to express value into the bracket exponential raised by theta x. And the third equation gives us the summation s ranges from 0 to n of moment generation function times PMF of binomial. In this bracket, we can see that p exponential raised to power theta into bracket all raised to power x because p and exponential raised to power theta x in equation 3 has s in common. That's the reason why we have this. And the last equation here, which is m into bracket theta equal to into bracket p exponential raised by theta plus q into bracket all raised by n, is binomial expansion. To find the mean and variance of binomial distribution using moment generating method, we are going to differentiate the last equation once. And when we differentiate the last equation there, that is our moment generating function, we have m raised to power 1, that is to say, that one means that we differentiate the moment generation function once, which gives us np exponential raised to power theta into bracket p exponential raised to power theta plus q all into bracket n minus 1 because we differentiate it once. And therefore, we now say that let theta equal to 0. And when our theta is equal to 0, the equation 2 gives us that np exponential raised to power 0 into the bracket p exponential raised to power 0 plus q into bracket n minus 1. In equation 3, we know that exponential raised to power 0 will be 1 by pressing our calculator. So therefore, in equation 3, we have np into bracket p plus q close bracket raised to power n minus 1. Based on binomial rule, we know that p plus q equal to 1. Our expected value using moment generation method of binomial equal to np. To obtain the variance of binomial distribution using moment generating function method, we have this. That is, our variance of s equal to differential of moment generation function twice into the bracket 0 minus into the bracket moment generation function when we differentiate moment generation function once all raised to power 2. And when we differentiate moment generation function twice, these are the process used. This is the result of when we differentiate moment generation function once. Now say by using product rule, we say let u equal to np exponential raised to power theta and v equal to into the bracket p exponential raised to power theta plus q close bracket all raised to power n minus 1. Now say that the u over the theta equal to np exponential raised to power theta. That is, we differentiate u and we differentiate our v also, and the result give us into bracket n minus 1 close the bracket p exponential raised to power theta open the bracket p exponential raised to power theta plus q close bracket all raised to power n minus 2. So this is the result of when we differentiate moment generating function of binomial twice. And after that, say that let theta equal to 0. So therefore, in equation 2, any place we see theta, we represent it by 0. And any place we see exponential raised to power 0, all will be equal to 1 by pressing our calculator. Equation 4 gives us np into bracket n minus 1 close bracket p open bracket p plus q close bracket raised to power n minus 2 plus np open the bracket p plus q close the bracket raised to power n minus 1. And we know that p plus q equal to 1 based on binomial rule. So we now have in equation 6 np into bracket n minus 1 close the bracket p plus np. So therefore, when we differentiate moment generation function twice and we make our theta to be 0, we have this n into bracket n minus 1, close the bracket, p squared plus np. So now we can find our variance of binomial distribution using moment generating function. We know that when we differentiate moment generation function twice, this is the result we obtain. And when we differentiate it once, this is the result we obtain. So therefore, by calculation, when we multiply this first one by n and p square, we have n square p square minus n p square plus this n p minus, when we use this square to open this bracket, we have n square p square. So by calculation, this one cancel this one, we have np minus np square. And when we factorize np out, we have np into bracket 1 minus p, and we know that 1 minus p equal to q based on binomial rule. So therefore, our variance of binomial distribution using moment generating function method is npq. The next distribution is Poisson distribution, and the PMF of Poisson is f of x into bracket lambda raised by x exponential minus lambda divided by s factorial. And this is the moment generating function formula. So by putting our PMF of Poisson into the equation, we have summation x ranging from 0 to infinity exponential theta x lambda raised to power x exponential raised to power negative lambda divided by s factorial. And when we factorize x out of exponential raised to power theta x and lambda raised to power x, we have into the bracket x into the bracket exponential raised to power theta lambda close the bracket raised to power x exponential raised to power negative lambda, everything divided by x factorial. So therefore, we factorize exponential raised to power negative lambda out, and we have summation s ranges from 0 to infinity into the bracket exponential raised to power theta lambda close the bracket all raised to power x divided by s factorial. And by using power series expansion for exponential function, from there we see that summation s ranging from 0 to infinity into the bracket exponential raised to power theta lambda close the bracket all raised to power s divided by s factorial equal to exponential raised to power lambda theta. So therefore, we represent everything here by exponential raised to power lambda theta, and this is the equation we obtain. And from this place, we factorize, and from this place, we know that exponential common to both of them. So therefore, we write one exponential, and this negative lambda, this is it, and this one we have 1 minus exponential raised to power theta based on exponential sum. For our moment generation function for Poisson is now equal to m into bracket theta equal to exponential raised to power negative lambda into bracket 1 minus exponential raised to power theta. So to obtain our expected value of Poisson distribution using moment generating function method, we need to differentiate our moment generating function we obtained before, which is exponential raised to power negative lambda into the bracket 1 minus exponential raised to power theta close the bracket. And to make it easy, we open the bracket and we have exponential raised to power negative lambda plus lambda exponential raised to power theta. So therefore, we differentiate this one and we obtain lambda exponential raised to power theta exponential raised to power negative lambda into the bracket 1 minus exponential raised to power theta back. So we now equate theta to be 0. That is when theta equal to 0. So therefore, any place we see theta in equation 3, we are representing it with 0. And in equation 4, we have lambda exponential raised power 0 exponential raised power negative lambda into bracket 1 minus exponential raised power 0. And this one gives us lambda times 1 times 1. As we know that exponential raised power theta equal to 1. So therefore, our expected value of Poisson distribution using moment generating function method is lambda. To obtain the variance of Poisson distribution using moment generating function method, we need to differentiate the moment generating function we got before in second time. And by using product rule, we have u times dv d theta plus v times du d theta. And we say that let our u equal to lambda exponential raised power theta and v equal to exponential raised power negative lambda into bracket 1 minus exponential raised power theta. By differentiate u, we have exponential raised power theta lambda. And by differentiate v, we have lambda exponential raised power theta exponential raised power negative lambda into bracket 1 minus exponential raised power theta. Based on this equation, we have u dv d theta plus v du d theta. That is how we get this equation 1. By when our theta equal to 0, any place we see theta in equation 1, we replace it with 0 in equation 2. Therefore, our equation 3, we have lambda into bracket lambda plus lambda. So therefore, the variance of Poisson distribution using moment generation function is also lambda. The third distribution is exponential distribution, and the PDF of exponential distribution is f of x equal to lambda times exponential raised power lambda x, where x greater than or equal to 0. 0 otherwise. And this is the moment generation function formula. So therefore, in this place, because exponential distribution is a continuous distribution, so therefore we have integral of 0 into infinity exponential raised to power theta x into the bracket the PDF of exponential distribution. So we factorize lambda out and we have integration of 0 into infinity exponential raised to power theta x into bracket exponential raised to power negative lambda x close the bracket dx. So therefore we factorize exponential out and we have lambda integration of 0 to infinity exponential raised to power into the bracket x theta plus into bracket negative lambda x close the bracket dx. So in the last equation, we represent into the bracket lambda minus theta x by b, and we differentiate that b with respect to the x, and we have lambda minus theta. So we want to make the s the subject of formula, and that's the reason why we have equation 3 here. So we just divide both sides by lambda minus theta, and therefore our dx equal to db divided by lambda minus theta. So therefore, any place we see lambda minus theta into the bracket x, we represent it with b by b, and any place we see the s, we are going to write db divided by lambda minus theta, and that is what we have here. So we factorize lambda minus theta out and we have lambda divided by lambda minus theta exponential integration of 0 to infinity exponential raised by minus b db there. And we can see that our integral from 0 to infinity exponential raised by b db vanished, because when we prove it further, we are going to obtain 1. So in the equation, that's the reason why we have lambda divided by lambda minus theta in equation 3. And that of equation 4, we just use lambda to divide everything. So therefore, our moment generation function equal to, into the bracket, 1 minus lambda divided by theta, close the bracket, raised to power negative 1. So therefore, when we differentiate the moment generation function of exponential distribution, once we have this one, and when we equate the theta into the 0, we have this. So therefore, the expected value of exponential distribution using moment generating function method is 1 over lambda. So we want to obtain our variance of exponential distribution using moment generating function based on the previous explanation by using product rules. We have this one. When we differentiate a moment generation function of exponential distribution twice, and when we equate theta to 0, we have this one. So therefore, when we differentiate moment generation function of exponential distribution twice, and we equate theta to 0, we have 2 divided by lambda square. So variance of exponential distribution using moment generating function method is now equal to 1 divided by lambda square. Thank you for watching. See you next time, and don't forget to subscribe.